This week's lab, we're discussing molecular spectroscopy, IR infrared, and NMR nuclear magnetic resonance spectroscopy. First, I will discuss IR with you. What you see here is a basic IR spectrum. On the right-hand side, what is known as the fingerprint region goes from 600 inverse centimeters to about 1325 inverse centimeters. That is the fingerprint region, which is distinct for each compound. Also, the ether signal appears in that region somewhere. Next, the one that you're going to be looking at, the one that's most important to you, is the carbonyl peak, C double bond O, which appears approximately around 1680 to 1750 or so. The C double bond O peak is a strong, broad, or a narrow peak, depending on concentration. If the concentration is high, then the peak is broad. If the concentration is low, then the peak is nice and narrow. It's very sharp. Next, you'll see a water peak. That should be around 3200 or so. The water peak is a smaller peak than all the other ones, and it's due to moisture or water in the compound. Next, the one that's important to you is the OH group and hydroxyl group peak. This is due to alcohols. In alcohols, what you will see is a nice, strong, broad peak around 3300 to 3500, depending on hydrogen bonding. If the OHs are hydrogen bonded to other alcohols, then the peak will be in the region of 3400 to 3500, 3600. Otherwise, it will be a nice sharp peak around 3300. The scale we use for IR is frequency. The units are inverse centimeters. On the side here, we have a basic scale. The basic scale describes to you exactly which peaks are due to which compounds, which functional groups. The functional group C double bond O, C double bond N, or C double bond C. Basically, any double bonded functional group peak will be in the region of 1500 to 2000 inverse centimeters. Next, between 2000 and 2500 inverse centimeters, you will see any triple bonded functional group peaks, i.e. C triple bond N nitrile or C triple bond C alkyne. Next, between 2500 and 4000, you will see an NH peak, or an OH peak, or a CH peak. You'll be able to determine which peak it is by looking at the empirical formula of your compound.
Okay. The next section in this experiment that we're going to do this week covers NMR. And the first thing we need to do is to discuss the degrees of unsaturation. That's the amount of double bonding going on in your molecules. And that affects your NMR spectra. We have two choices here. If I look at the first one here, this is the one we're going to be dealing with in the experiment, which is linear alkanes. They follow this formula right here. It's a CnH2 and plus 2. If you were to have a cycloalkane, for example, you would just have a CnH2n. These N's represent number of carbon, and these N's represent number of hydrogens. And another thing to keep in mind is that 2 electrons equals 1 bond or 1 saturation, as you'll see here in just a moment. Monovalent halogens. We're going to look at this one first. Halogens are monovalent, and we're going to treat each halogen, we're going to add each one to H, hydrogen, which is this part of the equation here. For example, I've got a C4H5Br3. If I add these 3 bromines to these hydrogens, I get a total count of C4H8. When I look at this, and I compare it to this linear alkane here, I'm short 2 electrons over here, because if I had C4H8 over there, I'm missing 2 electrons. These 2 electrons are in a unsaturated situation. You've got a double bond or a ring. Next, we're going to look at divalent compounds, compounds which contain oxygen, for example. When you do your hydrogen count for this, there's not going to be any change to the hydrogen count for each oxygen that you encounter. A good example would be C5H8O. And in that case, I don't count the oxygen, so I just have C5H8. And once again, if I look over there, I'd be missing 4 electrons. If I'm missing 4 electrons, then I've got either 2 double bonds or the formation of 2 rings. The last one that you're going to encounter in this week's experiment will be the trivalent nitrogen, or trivalent compounds which are nitrogens. For each nitrogen you encounter, subtract each nitrogen from your hydrogen count. The example I have, C5H9N, I've got 1 nitrogen, so I'm going to subtract this from the hydrogen, and I'll have a total count of C5H8. Once again, if I look at the linear alkanes equation over there, I'm missing 4 electrons, so that means I've got 2 double bonds, or the formation of 2 rings. In your case, you'll have 2 double bonds forming.
Next part of the NMR spectrum we'll be discussing is the delta scale. Delta is the chemical shift of a carbon. The scale runs from 0 to 8.0. At the 0 end here, we have a TMS peak. TMS stands for tetramethylsilane, which is the reference used in pretty much all the NMR spectra. Between 0 and 1.5, you will see a peak, which is due to a saturated carbon-hydrogen bond. A hydrogen that is on a carbon which is saturated with hydrogens will show up in this region. Between 1.5 and 2.5, a peak that appears would be due to an unsaturated carbon. That is a hydrogen on a carbon which is next to a carbon which is double bonded. For example, this carbon could be double bonded to an oxygen, to a nitrogen, or to another carbon. This hydrogen will show up between 1.5 and 2.5. The next region, from 2.5 to about 4.5, a peak is due to an X group and a hydrogen on the same carbon, where an X could be an oxygen, a nitrogen, or any sort of halide. That will cause the hydrogen to be downshifted between 2.5 and 4.5. Next, between 4.5 and approximately 6.5, a peak is due to a vinylic hydrogen, which is a hydrogen on a carbon which is doubly bonded to any other carbon, nitrogen, or oxygen, anything else. You will also note that around 6.2, 6.4, you will see a small peak due to dichloromethane. Sometimes dichloromethane is used as a solvent for your crystalline compound for which you're taking the NMR. Between 6.5 and 8.0, an aromatic hydrogen is shown up as a single peak. A hydrogen, which is on a carbon, which is in this ring formation, shows up in this region. Around 7.3, another small peak might be due to chloroform, CHCO3. This chloroform peak is due to the solvent. Chloroform sometimes is used as a solvent in the spectrum. An important note, OH and NH are singlet. They are not split by any neighboring hydrogens that may be on the adjacent carbon.
Okay, the next section of the proton NMR that I'm going to continue discussing is how the splitting occurs in the peaks. As Pervin mentioned earlier, the reference chemical is the CH3, 4 of those bonded onto a silicate, and that is your standard. And also, He also mentioned something briefly about how hydroxyls and so forth cause singlets. Well, this is what a singlet peak looks like. It's going to be a sharp single peak with no jagged edges on the side. And for things, they're due to the carbon bonded onto one hydrogen with no other hydrogens on an adjacent carbon, such as this one here. You've got one hydrogen here, and this R group is a carbon or some other functionality group other than hydrogen. There's a little counting rule that you set up for this, for a singlet, where you have N, which N is equal to the number of hydrogens on adjacent carbons. In the example I have here, there are no adjacent hydrogens, so that gets a 0. I give a 1 for the carbon having hydrogens over here. It doesn't matter if it's 1, 2, or 3 on this one. Each one gets a 1. And 0 plus 1 is equal to 1, and you form a singlet peak. Another peak that you might see would be a triplet. A triplet peak you would characterize by having 3 sharp peaks like this. And due to the same rules as shown over here, I'm going to count these 3 hydrogens over here as 1. I'm going to count the adjacent hydrogens on this carbon, and I've got 1 and 2. So if I count this up, I've got 2 plus 1 is equal to 3, and I get a triplet peak. This other one here is a little more difficult to look at. It's a quintet. It's got 5 peaks on it, and looks kind of menacing at first, but it's really not too bad. We're going to look at this carbon-hydrogen bond here as your main one. This is going to be your 1. It has 4 neighbors with hydrogens. 1, 2, 3, 4 on the other adjacent. If I do the same counting as I did earlier, I get 4 plus 1 equals 5, and that forms the quintet. You also have doublets and a bunch of other things that you might see with it.
Hi, I'll complement what Paul has just gone through about proton NMR splitting by showing you integration scale. This here is an integration scale. If you look here, you will see 1 peak, a singlet, with 1 bump on the integration scale. The bump represents the area under the peak. Next, you see 1, 2, a doublet. A doublet has 2 hydrogens, so it's 1 bump, 2 bump. Both of these bumps represent the area under both peaks. Next, what we have here is a quartet represented by the letter Q. 1, 2, 3, 4 peaks, so it's quartet. Count the number of bumps on the integration scale. 1, 2, 3, 4. 4 bumps represent the area under all 4 peaks. As you notice here, the bump goes up as it encounters an area under the peak, and then it levels off as there is no peak here. That means there is no hydrogens under the peak. Next, it does the same thing until it encounters all 4 peaks, and then it levels out again. Next, it's leveled out until it hits another peak. Here, it hits 1 bump, 2 peaks, 2 bumps, 3 peaks, 3rd bump. This one is a triplet represented by the letter T. As you can see, 1, 2, 3, triplet. I will discuss the 4 and the 3, the quartet and the triplet with you. Whenever you see a quartet around 3.5 or so, I believe, and a triplet, usually it is due to an ethyl group. Let me discuss that in slightly more detail. For example, you can write this as C, H, 1, 2, 3 H's on the adjacent carbon. For example, if you're looking at these hydrogens here, 1, 2, as Paul mentioned earlier, the N+1 rule, both of those represent 1. On the adjacent carbon, if you count the number of hydrogens, you will have 1, 2, 3 hydrogens. That will be your N. That's 3 plus 1. That's N plus 1 equals 4. A 4 is a quartet. Q, the letter Q. That is represented here. Why, you might ask, is it more downfield than this peak? Well, because this carbon has other substituents to which it is bonded. Now, if you look at these hydrogens here on the methyl, you will count 1, 2, 3, all of them are 1. They all get 1 total. Plus, N, the number of hydrogens on the adjacent carbon, 1, 2. So your N is 2. N plus 1 is 2 plus 1, 3. A 3 is a triplet. This triplet is represented here. 1, 2, 3, a triplet. And it is upfield because there's nothing else next to that carbon. Nothing else is bonded to that carbon. So it will be in this region. All the way at the end, this peak here is due to TMS. As Paul mentioned, that's your reference chemical, tetramethylsilane. And this peak is never used in the integration. You do not integrate the number of hydrogens underneath that peak. Thank you. Hi, I'd like to wind up by describing to you the procedure briefly. First, you would calculate the degrees of unsaturation as Paul described to you. You would look at your unsaturation, you'd say how many double bonds or how many rings you have present. Next, you look at the IR for functional groups. For example, when you see peaks on 3300, you have an OH, NH, a carbonyl on 1700 or so. You would determine which functional groups you have. Next, you would determine the structure of your compound. For example, how are the carbons, the oxygens, and the nitrogens bonded to each other? And finally, you would assign peaks to each hydrogen. Like I just showed you, you would take each one of your hydrogens, assign the relevant peaks to them, and that would wind up your interpretation of NMR and IR. I would like to thank you for your attention.